Hello and welcome back to the course on deep learning. Today we're finally at step number 4, full connection. So what is this step all about? Well, in this step, we're adding a whole artificial neural network to our convolutional neural network. So to all of the things that we've done so far, which are convolution, pooling, and flattening, now we're adding a whole new ANN on the back of that. How intense is that? That is something. That is definitely something. And so here we've got the input layer, we've got a fully connected layer and output layer. And by the way, the fully connected layer in the artificial neural networks, we used to call them hidden layers. And here we're calling them fully connected layers because they are hidden layers, but at the same time, they're a more specific type of hidden layers. They're a fully connected layer. In artificial neural networks, hidden layers don't have to be fully connected, whereas in convolutional neural networks, we're going to be using fully connected layers, and that's why they're generally called fully connected layers. And so basically that whole column or vector of outputs that we have after the flattening, we're passing it into the input layer. And here we've got a very simplified example just for illustration purposes. And what the main purpose of the artificial neural network is to combine our features into more attributes that predict the classes even better. So we already, in our vector of outputs in the flattened result from what we've already done, we have some features encoded in the numbers in that vector. And they can already do probably a pretty good job at predicting what class we're looking at, whether it's a dog or a cat, or whether it's a tumor or not a tumor, and so on. But at the same time, we know that we have this structure called the artificial neural network, which is designed, which has a purpose of dealing with attributes and coming up, or dealing with features and coming up with new attributes and combining attributes together to even better predict things that we're trying to predict. And we know that from the previous part, so why not leverage that? And that's exactly what the plan here is. So how about we pass on those values into an artificial neural network and let it even further optimize everything that we're doing. And so that's what we're going to be doing, but let's look at a more realistic example because this one is a bit too simple. So here we've got a better looking artificial neural network where we have 5 attributes on the input. Then we have, in the first hidden layer, we have 6 neurons. In the second, fully connected layer, we have 8 neurons, and then we have 2 outputs, one for dog and one for cat. And so an important thing to for us to talk about here is that why do we have 2 outputs? We are kind of used to having only one output in our artificial neural networks. Well, one output is for kind of when you're predicting a numerical value, when you're running a regression type of problem. But when you're doing classification, you need an output per class, except for the exception is when you have just 2 classes. Like we have 2 classes here, dog and cat, and we could have just done one output and made it a binary output and said 1 is a dog and 0 is a cat. And that would have worked totally fine. And actually, in fact, you'll see Hadelin do that in the practical tutorials, and that's how they'll be structured. But at the same time, if you have more than 2 categories, for instance, dogs, cats, and birds, then you have to have a neuron per every category. And that's why we're going to practice with 2 categories in this example so that we know what to expect if we ever have more than 2 categories. And so what's going to be happening here? So we've already done all the groundwork. We've done the convolution, we've done the pooling and the flattening, and now the information is going to go through the artificial neural network. So let's have a look at how that all happens. There's the information going through from the very start, from the moment when the image is processed, then convolved, then pooled, flattened, and then through the artificial neural network, all 4 steps. And then a prediction is made. And we'll see how this happens in a moment. It'll be very, very interesting. But for now, let's just say a prediction is made, and for instance, 80% that it's a dog. But it turns out to be a cat. And then an error is calculated, what we used to call a cost function in a artificial neural network, and we use the mean squared error there. Or in convolutional neural networks, it's called a loss function, and we use a cross entropy function for that, and we'll talk about cross entropy and mean squared errors in a separate tutorial and how all that happens. But for now, let's just say we have a loss type of function which tells us how well our network is performing, and we're trying to optimize it or minimize that function to optimize our network. So the error is calculated, and then it's back propagated through the network, just like we had in the artificial neural networks. It's back propagated, and some things are adjusted in the network to help optimize the performance. And the things that are adjusted are, as usual, the weights in the artificial neural network parts, so the blue lines that you see here, the synapses. Then also another thing that is adjusted is the feature detectors. So we know that we're looking for features, but what if we're looking for the wrong features? What if this didn't work out because the features are incorrect? And so the feature detectors, remember those little matrices that we had, the 3x3 matrices, they are adjusted so that maybe next time it'll be better, and let's see what happens, type of thing. But of course, it's all done with a lot of science in the background, with a lot of math, and it's all done through a gradient descent with backpropagation. So it's all not just random perturbations. It's actually very thought through how it's done. But nevertheless, the feature detectors are adjusted, the weights are adjusted, and this whole process happens again. And then again, the error is backpropagated. And this keeps going on and on and on. And that's how our network is optimized. That's how our network trains on the data. So the important thing here is that the data goes through the whole network from the very start to the very end. Then the error is compared. So the error is calculated and then is backpropagated. So same story as with artificial neural networks, just a bit longer because of that the first three steps that we already had. And now let's have a look at the interesting part, the really interesting part. How do these two classes work? Or how do these two output neurons work? Because before we've always kind of had one output neuron. What happens when we have two? How does this situation of classification of images play out? Well, let's start with the top neuron first. We're going to start with the dog. The main purpose, what we need to do first is we need to understand what weights to assign to all of these synapses that connect to the dog, so that we know which of the previous neurons are actually important for the dog. And let's see how that is done. So let's say, hypothetically, we've got these numbers in our previous layer, previous fully connected, or in the final fully connected layer. And again, these numbers can be absolutely anything. They don't have to be that. They can be any numbers. But just for argument's sake, we're going to agree that we are looking specifically at numbers between 0 and 1. So it's easier for us to argue these things and understand. And 1 means that neuron was very confident that it found a certain feature. And 0 is going to mean that that neuron didn't find a feature it's looking for. So because at the end of the day, these neurons, like anything else on this left side, is just looking at features at an image. This is already very, very processed, but still, it's detecting a certain feature or combination of features on the image, right? Before in the convolve step, we had kind of recognizable features. In the pool step, they're less recognizable. Then they become even less recognizable in the flattened image, and then they get combined and so on. But nevertheless, we're talking about here certain features that are present in the image or their combination. So a 1, which is being passed, and this is important, is being passed to both the dog and the cat at the same time, to both the output neurons. So a 1 means that for us, for our argument, it means that this neuron is firing up. It's really rapidly detecting that feature that might be an eyebrow. It might be detecting this eyebrow for simplicity's sake, is detecting this eyebrow, and it's communicating that to the dog neuron, to the cat neuron, saying, I can see my eyebrow, I can see my eyebrow. And then it's up to the dog and the cat neuron to understand what that means for them, right? And so in this case, which neurons are firing up? These 3 neurons are firing up. The eyebrow, and let's say the nose, is saying, I can see a big nose, and I can see floppy ears. So it's saying that to the dog and to the cat. And then what happens is we know that this is a dog. So the dog neuron knows that the answer is it is actually a dog. Because at the end we're comparing to the picture or to the label on the picture, and it knows a dog. So basically, the dog neuron is going to say, aha, so I should be triggered in this case. So these are my neurons. They're telling this signal that they're sending to me, to the dog, and to the cat is actually a indication for me that it is a dog. And throughout these lots and lots and lots of iterations, if this happens many times, the dog will learn that these neurons do indeed fire up when the feature belongs to a dog. On the other hand, the cat neuron will know that it's not a cat, and it will know that this feature is firing up, and this neuron is telling me it can see floppy ears, floppy ears, floppy ears, but at the same time, it's not a cat. So basically, to me, that's a signal that I should ignore this neuron. And the more that happens, the more the cat neuron is going to ignore this neuron about the floppy ears. And so basically, that's how, through lots and lots of iterations, if this happens often, so this is just one example, but if this happens often, maybe a 1, maybe a 0.8, 0.9, maybe sometimes it won't fire, but overall, on average, this neuron is lighting up very often. When it is indeed a dog, the dog neuron will start attributing higher importance to this neuron. And so there we go. That's how we're going to signify it. We're going to say that these 3 neurons, through this iterative process with many samples and many epochs. Remember, so a sample is a row in your data set, and epoch is when you go through your whole data set again and again and again. Through lots and lots of iterations, this dog neuron learned that this eyebrow neuron and this big nose neuron and this floppy ear neuron, they all seem to really contribute very well to the classification of what it's looking for, and which is a dog. So that's how it works. And again, these ears and nose and eyebrows, those are very, very approximate or like very far-fetched examples, because by this stage in this whole convolutional neural network, it is completely unrecognizable what they're looking for. But at the same time, it is something in the features of dogs or cats or whatever you're classifying. And then, so let's move on to the next one. Now we're going to look at the cat neuron. But these, we're going to remember that these weights are, we've sorted out the dog. So the dog is kind of like pretty much ignoring all these other neurons, 1, 2, 3, 4, 5, but it's really paying attention to what these 3 neurons are saying. Now, what is the cat listening to? Well, whenever it is actually a cat, right? This is an example of a situation when it's actually a cat. So you'll see that these 3 neurons, 0.9, 0.9, and 1, they're saying something to both the dog and the cat. And this is, again, important to remember. So this output signal goes both ways. It's the same, right? It's saying 1 to the dog, it's saying 1 to the cat. But then it's up to the dog and to the cat to decide whether to take into account that signal and learn from it or not. And both the dog and the cat can see that this is a photo. I should have put a photo of a cat here, but basically imagine a photo of a cat. Both the dog and the cat can see that this is actually a cat. So basically the dog is like, oh, okay, so these whiskers and these pointy triangle ears and this small size, I guess, or I don't know, oh, maybe this type, you know how cats have these things in their eyes? Their eyes are like little, they're not circles, they're lines or something like that, like cat eyes. Basically, these cat eyes, they're definitely not working for me. They're not helping me out predict, because every time these neurons light up, the prediction is not what I'm looking for. On the other hand, the cat is like, that's interesting. Every time this one lights up, or most of the time it lights up, it matches my expectation. It matches what I'm looking for. Okay, I'm going to listen to this guy more. Then this one, same thing. Every time it lights up, or most of the times it lights up, I happen to be rewarded for my prediction because I get it right. It's a cat. Okay, so I'm going to listen to him more. This one, useless to me because he's not actually, he's not even lighting up. It's a cat, but he's not lighting up. So the opposite is happening. And this one as well, it's a cat, but he's not lighting up, so I'm not going to listen to him. But this one, what was this? The cat eyes light up. I can see that it's a cat. It matches most of the time, so I'm going to learn from that, and I'm going to listen to these 3 guys more often than not. And so basically the cat is listening to these 3, and it's ignoring the other 5. And that is how these final neurons learn which neurons in the final fully connected layer to listen to. So the output neurons learn which of the final fully connected layer neurons to listen to. And that's how they understand. Basically, that's how the features are propagated through the network and conveyed to the output. And so even though these features, of course, don't have that much meaning to them, like floppy ears or whiskers, at the same time, they do have some distinctive, they are a distinctive feature of that specific class. And that's how the network is trained, because we also, during the backpropagation process, we also adjust the feature detectors. So if a feature is useless to the output, it's going to probably be disregarded, because this doesn't happen over one or two iterations. This happens through thousands and thousands of iterations. So with time, a feature that is useless to the network is going to be disregarded and replaced with a feature that is useful. And so at the end of the day, in this final layer of neurons, you're likely to have lots of features or combinations of features from the image that are indeed representative or descriptive of dogs and cats. And so then once your network is trained up, this is how it's applied. So this is the next step. Like, we've already trained up our network. Well, let's see what happens when this network is applied. So let's say we pass on an image of a dog. The values are propagated through a network. We get certain values. And so this time, the dog and the cat neurons don't know. They don't have the image of the dog here. They don't know that it's a dog or a cat. They have no idea what it is. But they have learned to listen to what is being shown here, right? They have learned to listen to, the dog neuron listens to these three neurons, the cat neuron listens to these three. And so the dog neuron looks at 1, 2, 3 and says, aha, these are pretty high, so my probability is going to be high that it's a dog. The cat neuron looks at these three and says, okay, this one is pretty high, but these are pretty low. Interesting, so my probability is going to be 0.05. And that's where you get your prediction. So then your first choice for this neural network is dog, second choice is cat, and that's pretty much it. So the answer is dog. And same thing happens when you pass an image of a cat. You get new values, and you can see that even though this one's high, these ones are low, and for the cat, this one's high, and this one's a bit low. So the probability here might not be as great as previously, but still you can see that it's a cat with 79%. And so therefore the neural network is going to vote that it's a cat. And so basically, the neural network is going to conclude that it's a cat. Voting is a term that is used for these guys. So these neurons in the final fully connected layer, they get to vote, and these are their votes. And again, we are just, for argument's sake, putting values between 0 and 1 here. These could be any values, but they get to vote, and then these weights are the importance of their vote. So this is these purple weights are how the dog neuron views their votes, how much importance it assigns to these neurons and to those votes, and this is how much importance the cat neuron assigns to these to the votes of these neurons. And so these neurons vote. The dog and the cat, based on their learned weights, they decide who to listen to, and then they make their predictions, and the whole neural network concludes that this is, in this case, a cat. And then that's your conclusion. And that's how you get images like this, where you have a cheetah, and then you have a cheetah class with like a high probability. So this is the probability that the network has predicted, and these are lows. But these still exist because there's still kind of like a small chance the other neurons are also listening to their voters, and they're saying, oh, maybe it's actually a leopard. And the bullet train, very, very probable. Here, scissors, this one won, but hand glass was very close second, and then frying pan stethoscope, because you could see like these guys, this neuron, the scissors neuron, the output scissors neuron listened to its voters, and it had the predominant vote overall, but then the hand glass had a good outcome as well. So there we go. That's how the full connection works and how this all plays out together. I hope you enjoyed today's tutorial. We're going to summarize all of this in the summary as well, and I'll see you next time. Until then, enjoy deep learning.